Hello, everyone. Welcome to Foundation Engineering. If foundation engineering is very important that we have to learn and practice throughout these semesters. If foundations are not properly designed and not properly constructed, your buildings will experience severe damages, and that damage is very hard to fix and to revise once the building gets damaged because of the foundations. Especially foundations are very important for weak soils where you have a big settlement going to against the vertical load on top of the buildings. And here we have two types of foundations, and we have shallow foundations and we have deep foundations. We're going to start with shallow foundations few weeks and before we move into the deep foundations. And there are some type of foundations, shallow foundations, as we see over there. The first type is simplest type of foundations, strip foundations, and spread foundations. Is a split foundations or wall foundations because this is one-dimensional foundations. It's like a one-way slabs. Whereas we have a two-dimensional foundations here, which is similar to two-way slabs. So this wall foundations is going to be stored along with all the long walls, and the spread foundations is going to be stored and designed and installed for supporting a one columns which receives a vertical load as well. And it's like we have another type of foundation which is similar to spread foundation. Actually, this is one of the spread foundation where we have a stepped foundation like that. And also we have a tapered foundation, tapered in order to provide more stiffness, strength to the foundations. And one of the interesting foundation is a combined foundations. Combined foundation supporting multiple columns more than two where we have a property lines just near the foundations so that this column will have a hard time to support the loading acting on it because we cannot extend the foundations over the other property lines so that we have another columns right there so that we have a big loadings over there try to balance these two foundations. So we have a type of a continuous moment situation over there. So you can balance these two columns by extending your foundations the opposite direction of the property lines. The last foundation is one of the most important foundation will be a bed foundations where footings is a big foundation. This is big foundations to support multiple columns on it. And we can see this foundation is very big, used to support a massive load of high-rise buildings or big buildings. So where we have very complicated moment diagrams and shear diagrams exist. So that we need some help from finite element analysis to calculate moment diagram and shear diagram to place levers in between. This is a two-way continuous beam. Our moment diagrams looks like that, which is calculated easily based on finite element analysis. And we're going to take a look at the finite element model later. Now we are looking at pressure distribution under footings. So the pressure distribution on the sand, it looks different from what that we have on clay. So this is, we have a peak distribution at the middle, whereas we have a large distribution at the edge right there. But both of these distributions are not very practical when we design building foundations. So the engineers make a uniform distribution of these ununiform pressure distributions. So it makes the design easier and practical. Okay, so the soil design, the foundation design especially, based on rectangular soil pressure by which we calculate the size of shallow foundations. Design equations are very similar to those from concrete design. So we have two types of design method. The first method is called allowable stress design, and second is limit state design. Limit state design is similar to the ultimate strength design in concrete as well. Here, the QA is the allowable stress for soil, and the A is the area of the footings, and PS is specific unfactored load acting on the footing. So this should be greater than the loading, as we all understand. Whereas we have a load factor alpha, and we have a phi factor, which is capacity reduction factor or resistance factor, to account for the uncertainty of the loadings. There are a few phi factors are recommended by ACI 318-02. We have some phi factors are recommended for certain circumstances. We're going to take a look at those phi factors as we proceed with the design. Things we should be very careful in designing foundation under limit state for design of foundations includes 6 factors, as you see over there. The first 3 factors are associated with soils, and the latter 3 factors are associated with structure, concrete, whatever structure itself. And the first criteria that we should be very careful in designing our foundations is a bearing pressure bearing failure, so that the soil should not fail under any vertical load acting on the structure. Next is a serviceability failure, so that the foundation should not interfere the serviceability of the buildings. It sits on shallow foundations. And also, if we have a excessive settlements, that must be avoided. And the 3 related with soil conditions, right? And the other 3 probably related with the concrete structure. First of all, the fractional failure should be avoided when vertical loading is acting on the structures. Also, shear failure must be avoided strictly. And the last thing is that anchorages should be adequate. The anchorages and lever details and developed lengths from a column to the footing or from the footing to the columns must be strictly designed well so that they do not ill behavior during taking vertical load. The allowable soil stress, which is QA, is calculated by dividing QLT by safety factor. QLT is the stress corresponding to the failure of the soil under the footings. This is usually calculated based on foundation slip failure, as you see over there. The QLT calculations are very difficult and not easy, so we probably skip the discussion of the QLT calculation with associated dislocation of soils for now. Where the FS stands for a safety factors. So safety factors must be properly established to get a QA. QA is something that you can use for design with the safety. We can also refer QA is a bearing capacity of the soil. This is one we understand very important parameter, has very important parameters. QLT is another one, is a failures at soils based on soil dislocations. We will take a look at very simple loading cases on foundations, especially on shallow foundations. And suppose that we have a shallow foundation, something that you see over there, and where we have a vertical load and also we have a overturning moments. Due to the overturning moments, we will develop a tension side and compression side. The stress diagrams looks like that. This is tension, this is compression, and this tension and compression will change when you change the overturning moment. So this is pure bending circumstances, and where we have added stress, rectangular stress, compressive stress blocks due to the vertical load. Here, I'm going to change the color here. Okay, you may have a vertical force here. Accordingly, you have a compression block. If you superimpose this compression block into the bending stress distributions, then we will obtain resultant stress state as you see over there. We have some a little tensions, compressions over there. If the compression block overcome the tension overturnings over there, which means that we do not have a overturnings. So the vertical stress due to vertical load is greater than the tension stress due to overturning force. And we have increased compression stress at the other side where we have added compression due to vertical load and compression again due to the moment. We studied this from mechanics of materials, sophomore colleges, where the loading falls into this little diamond area. We call that kern dimensions. Then this structure will never experience overturnings. Everything is going to be transferred to compressions on the structure. So This is important. The reason where, in case where you don't want to have a tension overturning situations. Now let's calculate bearing pressure on the foundation, which is Q over there. That the Q is composed of axial load, vertical axial load, and stress due to the overturning moments. So that the sigma, which is from vertical load, can be calculated P over A, and we have a my over I value for counting for overturning moments. Now we have a plus and minus case depending on the direction of the moment. This is very easy to calculate, and very fundamental. And in every shallow foundation, all we need to calculate is the values and corresponding bearing pressure, so that we understand how much pressure is acting on the soil, which the allowable bearing capacity already, and compare them to decide the proper size of the foundations. When you have that, you will end up with these loadings on the foundation. First of all, this is your soil bearing capacities. Soil bearing capacities, which means that how much pressure can your soil resist against the loading which is applied on the foundations. And your externally applied load has two types. The first type of loading, of course, is the vertical loading. It's fundamentally important loadings that you want to resist against. And also you have loading that's from concrete weight itself. Okay, this is another loading on the soil that you're designing. And there's another loading that you must not forget is the soil loading on the top of the foundation. This is another soil pressure, depending on how deep your shallow foundation is being installed. And there's another one there that you should not forget is surcharge loading. These surcharge loadings are the loading from on the ground. Surcharge. So this is a traffic loading here. This is a pedestrian loading here. And all the loadings are found on the ground level as called a surcharge loading. So you need to subtract all this loading acting on the soil from your soil bearing capacity to calculate your net soil pressure. So this net soil pressure is the soil pressure you want to take a look at when you design buildings. Okay, we're going to take a look at one example how to calculate the soil pressure later, but it is very easy as long as you understand the differences of the loading on the soil. Again, you have surcharge on the top of the street, and you have soil loading bearing your foundations and your foundation concrete loadings. These are external loadings that you need to subtract from the soil bearing capacity to get a net soil pressure. Okay, take a look at simple example how you calculate net soil bearing pressures here. And these foundations are 2 feet long. I'm sorry about the unit. This is not SI unit, but okay, you can always transfer to SI units. Sorry about that. And you have 3 feet depth deep soils, and you have, of course, primary vertical loading that your foundation must resist. And again, you have a soil allowable bearing pressures. That is the pressure that you can have from soils based on some type of test or calculations. This is usually given from soil engineers for structural engineers. So we should not worry about that much. All right, now the important thing here to know the soil bearing capacities, which is net soil bearing capacities. To compare this soil bearing capacity to the loadings, to judge whether your soils are under control or not. I mean, the bearing capacity is greater than the loading from top, then you're okay. Otherwise, you're not okay. You have to do something else to reduce. If the soil allowable soil bearing capacity is smaller than the loading, the stress caused by the loading, you should do something else to reduce the stress from the loadings. For example, you can extend the size of the foundation to reduce soil bearing stress, which is coming from the top, or you can have a soil compactions to increase the soil bearing capacities. So before you decide what to do, you need to know the soil bearing capacities, which is net soil bearing capacities. Okay, what is soil bearing capacities? The allowable soil bearing capacities given in these problems. They are given as a 10,000s. What's the units? PSF. Sorry about that again. Pound per square foot. You can transfer this to the SI unit later when you review this video clip. And this is soil bearing capacity. That's given by the soil engineer. So you really don't have to worry about that number. So we will receive this value from separate soil report. But we cannot use this soil bearing capacity because we have some other loadings and stresses coming from concrete and coming from surcharge. As I told you, surcharge is the loadings coming from underground, which is traffic and pedestrians loadings, all that. So that we have to subtract all this loading from our capacity, which is bearing capacity, to get net bearing capacity. Is very important. Okay, so this is a concrete weight. The concrete density times thickness gives you stress units that can be compatible with soil bearing capacity, pound per square foot, right there. And also you have to subtract all these pedestrians and traffic loading, which is called surcharge. So we end up with a 9,225 PSF. Okay. Now we're ready to compare this value to the loading, to the stress caused by the loading coming into the foundations. Okay. Or you could divide the vertical loading by this value to get required area. See, your force P equals stress times A. So we know this. This is course net bearing capacity, so that the required area of the foundations can be easily calculated by dividing the loading over sigma, which is net bearing capacity. Now you end up with the size of foundation initially. and we have to check from there on a few things more, but this is very important first step that you have to go through. Now, we are looking at 3 types of stress that is acting on the foundations. The understanding of the stress on the shallow foundation is very important to design rebars and details on the shallow foundation. This first case where we have a bigger axial load than the stress is caused by the overturning moment. Here, all the stresses remains compression because the stress from vertical loads, axial load, is greater than the stress caused by the overturning moment. The second case, but the last case is the other way around. The stress is caused by the overturning moment is greater than that of from vertical load, so that we will experience some tension region over there, which is very bad for foundation, because foundation is going to lift up. It's going to cause a lot of problems building which is sitting on the top of these shallow foundations. So this is the case where we have to take a look at very closely. And the case in the middle is where we have a zero right there, which means that we have exactly the same situation for the stresses from the vertical load and stresses from the overturning moment are identical. Okay, these 3 cases must be carefully looked into design and sizing the foundations. So this is the case from the case where the vertical stress caused by the vertical load is greater than the stress caused by the overturning moments, which is case number 1 over there out of 3 cases. But the other cases where the stress is from overturning moment is greater than the stress from vertical load, and we'll have a little difficult problems. And we're going to take a look at how we're going to cope with that case. Now let's take a look at a case where we have a stress due to the overturning moment that's greater than the stress from vertical load. And there, as we saw already, we have a tension zone underneath the foundation, makes the foundation cripple. So we cannot use really foundation, and this portion cannot be used as a foundation because we have some overliftings in these tension regions. So this is not very welcome. So we have to resize the foundation size to account for these tension zones when we have excessive overturning moments. Now take a look at the foundations and the soil bearing pressure profiles. And as we see before, we cannot have a load bearing capacity at these regions where we have tensions. So that we only have a compression zone right there where soil support foundation and buildings. So this is the pressure block where we can have a support the foundations. Now we really need to know what soil pressure on this particular region. So we have to know this soil pressure, in order to compare with that with a allowable soil bearing pressure. If the allowable soil bearing pressure is still greater than this soil pressure, then we're okay. Otherwise, we have to do something else, such as increasing the foundation's size or reinforce the soils underneath the foundations or whatever appropriate to provide a appropriate soil foundation. Now, how can we calculate soil pressure on this particular stress block? Okay, here Let's just assume that this is a boundaries where soil goes into compression or soil goes into tensions. And we assume this is divided into three R's, where R is the edge distance between loading and the edge of the foundations. Okay, this is R, 3R. So what happened here? Okay, let me change the color. Okay. Okay. This is a boundaries between tension and compressions, and these all R's. Okay, this is the case where we have a big eccentricity, which is E3 over there. Then we start having a overturning moment, as you see over there. When you have a overturning moment, which means that we have some separation between foundation and the soil, which makes also the foundation useless in that particular regions, and this is very bad. So we have to redesign the foundation. We have to introduce a bigger size of foundation to see if the Pmax, the soil bearing pressure, is less than the allowable soil bearing capacity. So here, when you have a overturning moment, which is greater than the compression force on the foundations, then we will have a uplift of the foundations. When you have uplift of the foundations, you see something like this. In this area, we have a separations. So which makes the foundations useless. See, because this is not foundation anymore if we have separation from the soil. This is soil. Okay, and this is foundations. And this happens because of the big overturning moment due to the big eccentricity, something like this, right? So we have to do something about it. Now, what can we do is that we can redesign the foundation size bigger so that we can prevent overturning moment. How can we do that? So here, if your loading falls in outside of the current boundary, then we will have a overturning moment. And the current boundary is defined as L over 6. This is L over 6. This is L over 6. So the entire diameter of current boundary is L over 3. And if your load is falling on the boundary or less inside the boundary, which is L over less than L over 6 or is equal to L over 6, your foundation will not rotate. Well, in this case, will rotate. Because we have overturning moment is greater than the vertical load. Okay, so this is something that we should prevent from happening. In other words, we have to prevent the overturning moment in the foundations by making a larger foundations so that the soil bearing capacity, allowable bearing capacity, should be greater than the soil pressure on the foundations. Okay, when this happens, when overturning moment is greater than the vertical load causing a lift or separation of the foundations from the soil, then we should be able to make a large foundations so that new soil pressure on large foundation. This is new soil pressure on the large foundations. Large foundation should be less than the allowable soil bearing capacity. We could say allowable soil bearing capacity. Okay, this is what we should do. This is what we should do. Alright, then what we can do is this. Okay, this is the original foundations right here. This original foundations will be separated here in this region. This is tension region because your overturning moment due to this is eccentricity right here. This is eccentricity. Due to the big eccentricity, so the foundation will rotate this way, isn't it? Will rotate this way, so that we have some separation or uplift in this region where we have to ignore this part of foundations. So this is not foundation anymore because of the excessive overturning moment in this directions, right? Then we have to enlarge foundations. Something bigger than that. Like this. And we have to adjust the foundations so that the vertical load coincide with the center of the triangular compression load, as you see over there. So the load from above is passing through the centroid of the compression block. Compression block is the soil bearing, which is the compression force which is acting on the soil. Soil bearing block is the compression force acting on the soil, and this foundation is adjusted so that the load, external load from columns or buildings going through the center of the compression loading block. Do you follow me?